right. So 4.1, starting off. Go ahead and put today's date up top. So absolute extreme values. Absolute means the very, very highest and the very lowest. Absolute meaning there is nothing higher or lower than this point. So, an absolute, because you'll hear about locals, an absolute maximum value only happens when, given that y value, it must be bigger than or equal to all the other y values. So if I write f of c or f of x, that means y values. If I want it to be a minimum, then f of c has to be less than or equal to. Yes, there's an equal to the rest of the y values. So that's all it says. Other ways that I'll say absolute extrema, global. Okay? Global extreme values or global extrema, absolute extrema. That means the same thing as absolute extreme values. So those are words that you do need to know. Extreme values are located in the interior or at the endpoints of a function. Maxes and mins, that's the way we can think about it. Maxes and mins happen inside the function or at the ends of the function. So far all I gave you were some quick definitions. You don't have to know the exact definition, but when the AP test wants to say maximum, sometimes they'll give you definitions instead of the word maximum. That's why that's there. All right, so I have just x squared. What's x squared's domain? All real numbers. So given that this is all real numbers, does this function have a minimum? Yes. Here is your minimum. The minimum occurs at x equal to 0. The value of the minimum is the y value, y equal to 0. So the minimum happens at x equal to 0. If they ask you for the value of the minimum, that would be the y. It would be 0. Does it have a maximum? No. So if I asked you about this function, you would be able to tell me this very simply, very easily. This one has endpoints here and here. I'm making the function go from -1 to 2. So it's the same function, only now I've chopped the domain. I've now said I don't want you to use all real numbers. I want you to use -1 to 2. So now that I do that, is there a minimum? Yep. At x equal to 0 still, what's the value of the minimum? Y equal to 0, or you could just say 0. Does this now have a maximum? Yes. At x equals 2 with a value of, it says value of 4. Perfect. So now that I changed the domain, I've just changed the problem. I made it have a maximum. Okay? We're going to go through a bunch of definitions today, and then you're going to be doing pretty much most of your stuff algebraically, and then I'm also going to get you to do a little bit of algebra to prepare for tomorrow. So starting off, you're going to learn a theorem, and you'll notice in your foldable there's a tab for this theorem. This is the second theorem that you're learning. What's the first theorem we learned? Intermediate value theorem. Can someone raise their hand and give me one of the conditions that must be true for IVT to be true? James? The function must be continuous. Jitesh, what's the other one? It must be closed. Continuous, and the function must be closed. Can someone raise their hand and tell me what it then guarantees? Let's see. Adriana? They exist. So, given an endpoint, given another endpoint, as long as the function's continuous, I guarantee that every single y value between those endpoints will exist. Could a y value happen outside of that? Yeah. Is it guaranteed, though? No. So guarantee is a very special word. It means no matter how I draw the function, no matter what function I make, you guys could all make 30 different functions, I can guarantee that because of IVT, from point A to point B, those y values will be used. But some of you will draw functions that use more, and that's okay, but it's not guaranteed. So I gave you here EVT, if a function is continuous over a closed interval. So just like IVT, you need it to be continuous on A to B, which is a closed interval. So the continuity only matters within A to B. Some of you had a really hard time with that. I don't care if there's 30 vertical asymptotes before A. That doesn't matter. From A to B is all I care about. All right. So we wanted to talk about interior and endpoints. So on this graph here, I have a maximum at the interior of the function. I have a minimum at the interior of a function. But the second one, there's a maximum, but it's at the endpoint. And there's a minimum, but it's at the endpoint. And then this guy, there's a maximum on the interior, but a minimum on the endpoint. So those are just ways that you could have maxes and mins. We're going to start comparing the derivative to this. So local maximum is a maximum within some open interval. So local is not the same as absolute. A local means as long as it's the maximum or the minimum in that little neighborhood. So in bright green, this guy is a local minimum because it's the lowest point for that part of the graph. And then this guy right here is a local maximum because it's the highest point for that part of the graph. And then same thing here. That's a local minimum because that's the lowest point for that part of the graph. So when we start looking at graphs, we're going to start talking about derivatives. Which one? This one? That's the lowest. You graph this and you go down to that point, so it has to be the lowest. It's the lowest here. So if I go like this, do you see it now? So it's the lowest over some interval. Okay? All right, so this guy, make an F prime sign chart for this guy right here. And yes, we'll do endpoints. Those are not going to continue on. So those are endpoints from here to here. So let's talk about this theorem. So we know two things are needed just like IVT. So if IVT is true, now you know that EVT is true, extreme value theorem. So we're just going to learn it exactly the same way. So, DeWitt, give me one thing that is needed for EVT, extreme value theorem, to be true. Has to be continuous. Gustavo, what's the other one? Closed. And remember, the continuity only depends on that closed interval. So EVT, what it guarantees? Guarantees max and min. It guarantees that as long as it's closed and continuous, you will have not only a max and min. I'm going to add the word here. So right here it says everything. You're actually guaranteed absolute max. This is a big fat and absolute min. You're not guaranteed just random max and mins. You're guaranteed absolute, not locals. You can have locals, but you are 100% guaranteed that you'll have an absolute max, and you are 100% guaranteed that you will have an absolute min, both. Not one, not the other, both. Okay, so that's what EVT. So IVT guarantees us Y values on that domain. EVT guarantees us absolute max and absolute min, and I want you to make sure you always say that word and. So this guy, what was going on right here? Vertical tangent, so the derivative there is undefined. Right here, what's that called? The horizontal tangent, which does give me a derivative 0. What about this guy here? Horizontal tangent, 0 here. What about this guy here? Cusp, so the derivative is undefined. And then this is questionable. I think I could take that. Horizontal tangent, I'll take it. It looks like it. All right, double check your sign chart. If I'm going up, what sign should I have? Positive. I'm still going up. Going down. Going down. Going up. All right, so We're going to talk about this. I just wanted to kind of review doing the sign chart. Does EVT hold? So what are the two things we need? Closed. Is this guy closed? Yes. Is it continuous? Can I draw from here all the way to the end without ever picking up my pen? Yes. What are the points that you think about when you talk about continuity? Undefined continuity would be holes, removables, infinites, oscillating, and jump. What do you think most people confuse with them? These little U's. That's what's going to get you confused. Do we care if the derivative is undefined? No. We didn't even talk about derivatives yet. So I wanted to show you that this graph has undefined derivatives. EVT holds. So what am I guaranteed? Absolute max and absolute min. And you can physically see them. Here's my absolute max right here. Here's my absolute min right here. I can physically see them. Do I have other maxes and mins other than absolutes? So let's label those also. We'll call those locals. So what's this guy? Local min, because it's the lowest. Is this anything special? No. Is this guy? No. How about this endpoint here? Yes, that's a local. Max, because it goes up to the point. Alright, now that we got all that, I'm going to show you what it looks like on a sign chart to have a maximum or a minimum. We're going to start off with interior because it makes the most sense. Draw yourself a maximum, just in the air. So draw from left to right. You have to create the maximum. So most of you are either doing one of these, or like a zoop. So what happens before the maximum? Yeah, it has to go up. And what happens after the maximum? Has to go down. If that has to happen, then for a maximum, your F prime interior point, then you have to go up first. So what's the prime for up? Positive. And going down? Negative. And here's the confusing part. Your derivative can be two different things. It can be 0, and it can also be undefined. Can someone tell me how I could have an undefined derivative, but it still be a maximum? A cusp would be one good example. Corner would be an example. How about vertical tangent? You're saying no, but I want to know why. Khalid, why? You go down and then you keep going down, or you go up and then you keep going up. So that's how you know that a vertical tangent will never be a max or a min. Alright, so that's actually what it looks like every single time you have a maximum. And you're going to see on your tests, on your questions, it'll say explain your reasoning, give justification. What you will write every single time this happens, you will say F prime changes from positive to negative, and then you'll also tell me how much the prime is. It'll either be 0 or undefined. That's your reasoning. I don't ever want to see a sentence. I don't want to see a paragraph on why you believe it's a maximum. It is a maximum because this is my reason. I have to be very clear about this. You are not permitted to do a sign chart and leave it. If you have a sign chart that's not reasoning, give yourself notes on that. This is not considered reasoning. This down here is. It's the same thing as your sign chart, but the AP needs to see it in words, which means I need to see it in words, and you will lose a point every single time you forget to explain. And this is your explanation in purple. So that should make it a little easier for you to do a minimum. What happens for a minimum? Negative, positive, and same thing. It could either be 0 or undefined. And your reasoning would be F prime changes negative to positive, and F prime of wherever that is 0 or undefined. Endpoint's a little bit trickier. So let's do a maximum. So we got to do endpoint for the left and for the right. Left is easier. Start left. Put your finger in the air. Make it a maximum. Where do you have to go from there? You have to go down. There's no doubt about it. You have to go down. So what does the sign chart for f prime look like for a left endpoint? It just has to have a negative. Now, given that point that you went down from, at that point, was the derivative anything special? Was it 0? Does that look like a 0 derivative? No. I'll do a better one. Constant. It's constant. Is that derivative at the endpoint anything special? Not 0, not undefined. It's not special, and that's why we don't have any number above it. There's no number above it because it's not special. It's not a 0, it's not an undefined. So, it could be. Actually, the example I did before this, it was. In this case, it doesn't have to be the rule. All right, right side endpoint. What's the only way the right side endpoint could be a maximum? You got to go to the max. So it has to be positive. All right? And then left and right this way. Now it should make sense. So left side, if I want it to be a minimum, then where does it have to go after? Make a point and make it the minimum. Has to go up. So it has to be a positive. How about right side? Then it has to go down. Please don't memorize these. That's a waste of time. You should be able to see if there's a plus, that means the graph is going up, and you should be able to tell that that's ending at a point high, which means maximum. It is a waste to memorize these. You should be able to tell. So, you would just literally say this is a left endpoint, and f prime negative after. I'm going to essentially do that for all of them. That's our reason. This is a right endpoint. And f prime positive before. And then from here, you guys can fill out the other two. That's how you explain. You restate your sign chart with words. Barely any words. I want this to be fast. I don't want you to waste time with it. Okay? Let's see. So, Douglas asked me about critical points. Critical points are defined as f prime of x is equal to 0 or f prime of x is equal to undefined. Big hint here though, critical points, not always max or mins. Just because you have a critical point doesn't mean you have a max or a min. Okay, so these are my two examples. I have a critical point here because we can make a sign chart. I'm just going to squeeze it right underneath. Where's my critical point on x cubed? At 0, what is the derivative at 0? It is 0. That is a critical point. But, what's the sign chart before it? It's going up. Hello, sign chart before? Positive. Sign chart after? Positive. That's how you can tell. I don't need to see a picture. I can tell from your sign chart this is not a max, this is not a min. Same thing here. This is another critical point. At 0, what's my derivative? Undefined, because what's happening there? Vertical tangent. My derivative before? Positive. My derivative after? Positive. Can't be a maximum or a minimum because they don't change. So, critical point, people get a little bit confused because they always believe that critical points mean max and min. But we just showed you two where they're not. So you really have to think about, does your sign change? So, can you ever prove max and mins without a sign chart? No, you better always have one. I don't want to see guessing. So there's a few quick sign charts I want you to understand. There is a difference between this and the one at -3. So this is how I want you to do your sign charts. And I can even put signs. What's happening at 5? Why did I cross it out? What do I make you guys actually cross out? Discontinuities. So what is your mind thinking about? We already went through them. Removable, jump, infinite, oscillating, that weird one we don't really talk too much about. That's what your mind's thinking about. So is it possible for this 5 to ever be a maximum? Or a minimum? No. It went from negative to positive, so if you have trouble remembering, negative means coming down, positive means going up. You can actually draw the graph on top of your sign chart here. So I would go up, and then down, and then up. That looks like a minimum. This is why I want you to cross out those values so you never use them. You don't ever use these because they don't exist. There's an open circle or there's a vertical asymptote. You can't use them. But what's happening here? Is this a max or a min? It's a maximum. What type of point is happening that it's undefined? What type of point? It can only be 2 of them. It can only be a corner or a cusp. Because the sign change? That's why I wanted you to know those definitions a long time ago. Samiza? I'm telling you, if you see a sign chart and they're crossed out, it's the same thing for you. If you have a removable discontinuity at x equal to 5, when you do your sign chart, removable discontinuity means derivative doesn't exist either. That's why it has a u. But it's crossed out because the point doesn't exist. We cross it out so you never get confused thinking that's a minimum. Okay? That's probably the major thing that I wanted you guys to know from there. The last piece is just finding domains. I'm going to do one of them for you. I'm not going to have time to go through all of them for 5th period. I'll try to go faster. I can't promise it. Domain issues, you have a total of 3 domain issues. First one, x in the denominator. If x is in the denominator of a fraction, you got an issue. X under even root, or x with an even root power, 1/2, 1/4. Okay, the denominator of the power has to be even. So let's say 2/3. The denominator is a third. That means it's a cube root. It's odd. If it said 3/4, now that's an even root. Okay, and then this guy, x in log or ln, either of those two. This is just a combination problem here. So e to the x, do we have any domain issues for that? No. But if I do e to the square root of x, because of the square root, now we do. We're going to start combining. So I'm going to do this guy. For every single one of them, they're exactly the same. You figure out where the issue is. So this guy, here's the issue. The -3 I don't care about. That's the issue. The x is inside the ln. So you start with your issue. We've done it before. We're going to set it equal to 0, and we get 2 values. So your sign chart that I'm doing here is not for the whole problem. It's only for the inside. So I'm doing the sign chart only for the x squared minus 25 part, the inside part. So if I put -5 into there, it's 0. If I put +5 into there, it's 0. If I put 0 into it, it's negative. If I put -1 million or +1 million, becomes positive. And then you just ask yourself, that was the inside of ln. What is ln allowed to use? ln is allowed to only use which ones? Positives. So here's your domain. Here's your domain. Why is that helpful? So when you do your derivative, I guarantee you this, you better not have any derivative values from -5 to 5. If the function doesn't exist, then the derivative cannot exist. Can this ever be a max or a min at -5? No, because when you do your derivative, it's going to be undefined because the point's undefined. This is the domain, tells you also where your derivative potentially could be. Does that make sense? I will try and get through the other ones. If I don't finish them in class, then I'll have both videos, so we'll see.